My name is Steve Murtagh from Etsy, and I'm going to talk about our experiences looking beyond TF-IDF for other ways of doing similarities. So it helps to know a bit about Etsy, both as a site and our engineering culture. So we are the world's handmade marketplace. Anyone can sign up, basically open a shop, pay a nominal fee, and list an item. The only real restrictions we have are the items you list must either be handmade by you or they must be vintage, meaning more than 20 years old. So we end up with some interesting problems. We don't have SKUs, we don't have anything like that. Most of these items are one of a kind, will never be seen again. And currently we have about 20 million active items in the marketplace. About 80% of these are handmade by about 1 million active sellers. And it's hard to stress enough that we don't control the content on Etsy. We just provide a platform for other people to sell things. So this is a somewhat typical Etsy listing. A nice photo, nice ring. It's an engagement ring inspired by the heart meter from The Legend of Zelda, out of diamonds and platinum and rubies, so high-end and geeky at the same time. The title, which is this, it's not a good place for it, a huge blob of text at the top, is partly a title, partly them trying to squeeze some extra terms in there, trying to game our relevancy algorithms. There are literally people whose livelihoods depend on their ranking in our search results and their ability to make sales based on that. So we have some very dedicated sellers who try and game our relevancy algorithms to get to the top. Our search is really a very important part of the site because users can put pretty much whatever they want in any of the fields. It's hard to go through all that. You can't really make a taxonomy of 20 million items. We have 15 million user-driven searches a day, just somebody going to our search bar, typing in a query. We end up with about 80 million calls to Solr. We use a couple to populate the search page, one for the main results, one for ads. We have a variety of other sources that we call out to Solr for. Etsy engineering is something we publicize a fair amount in our Code as Craft blog. We're very big proponents of continuous deployment. We push our web stack, which is a pretty basic LAMP stack, maybe 30, 40 times a day. Pretty much half our company is engineers, and anyone can push to production at any time if they really wanted to. This is less continuous, but still possible in our search stack, which is Murtagh, Solr, and Lucene. Mostly because we never have more than about half a dozen to a dozen people working on it at any given time. We can still probably push it 10 or 20 times a day, depending on how many re-indexes we require. As you'll see, we have a very experiment-driven culture. We usually don't get decrees from on high. This feature must launch at the end of this 60-day sprint. Come up with ideas, get out some minimal testable product in production, run A/B tests, side-by-side experiments, Mechanical Turk, and just see what this does. Is this helpful? Is this a good experience? Sometimes we say, you know what, we don't care, we're going to push it anyway, but by and large, we at least run the experiments even if we know we're going to ignore them. We also really like hybrid engineering roles. We talk a lot about DevOps, product dev. All of the people maintaining the search cluster are also the people tweaking the relevancy algorithms, also interfacing it with the PHP code. My background is actually academia. I am and probably always will be a PhD candidate in computer science focusing on machine learning. Great job dropped in my lap. It's hard to go back and finish my dissertation. But so I come from a machine learning, data science-y background. But at the end of the day, I still roll up my sleeves and go into the guts of Lucene to write some code, which keeps life a little more fun. Our search infrastructure is not terribly exciting right now, actually. We have 2 search clusters, Flip and Flop. They each have a single master and 20-ish slaves, I think. Only one of these actually takes traffic at any given time. The other one is completely dark. So when we want to do a deploy, we push to the dark cluster, say Flop. If we need to reindex, we run the reindex and then literally flip a switch, and all the traffic gets diverted to Flop. Flip is then dark. We can push the same code, rsync the index over. This lets us really quickly make changes to the cluster. We can bounce all the slaves in parallel because we don't have to worry about serving requests. We don't actually use Solr's HTTP service. We use a package called Thrift, which is basically a nice, fairly small cross-language RPC framework, which has some benefits. We can do retries and make sure that a slave isn't GCing before we connect to it, but we lose some flexibility. One of my colleagues talked last year about our replication. We actually use BitTorrent to replicate out to our slaves, which has all sorts of benefits, including none of the problems that come with multicasting. We just moved to Solr 4.1 after a fairly lengthy reconciliation process. And we do incremental indices every 12 minutes or so. It may take up to half an hour for a change made by a seller to propagate out to this, the search stack, but it's not, we care about the responsiveness on the buyer side. If it takes 400 milliseconds, we might lose a sale if it only took 200 milliseconds, but if it takes 5 minutes for you to tweak a comma in the title of your listing, it's less of a concern. So on to the meat of the talk. I said we are looking beyond TF-IDF. First question is really why? It works really well, and there's a reason why it's pretty standard across information retrieval, even though it's probably an older technique than I think anyone in this room. So this is what a search page looks like on Etsy. We have our core search results down here, just some function of the quality of the item, how relevant it is to the query. Some other things are factored in there. We have a row of ad results, which are also powered by Solr. It's just paid placement instead of necessarily relevancy-based placement. Some standard fasting stuff on the side, nothing terribly exciting. And for this query, unique bag, you see pretty much what you'd expect to see, a lot of kind of funky handmade bags. Even the ads are pretty relevant to it. So it looks good. But even for this, on the first page of results, if you scroll down a little bit, you start to see some weird things. So up here, we have a pair of luggage tags. Very clearly luggage tags, not a bag in any way. Down here, we have a nice handmade unique bag. And so the question is, why are these luggage tags being ranked higher than an actual bag? This is really kind of a weird experience for a user. If you type bag, you're looking for a bag. You're usually not looking for something to go on a bag. You might type in bag accessory. And this isn't unique to this query. There are a lot of queries like wedding dress, desk, where we get all these strange results that are like complementary products maybe, but not actually what the user wants. But to figure out where this is coming from, we actually have to dive really deep into the guts of the system, all the way down to Lucene's practical scoring function. Guessing 99% of people using Solr and Lucene have this as their base relevancy algorithm. It's just a very simple TF-IDF implementation. So we have a query, and we want to find the score of a document for that query. And it's just broken down like this. So first we have a coordination factor, which is the degree of overlap between the query and the document. A query norm. Then for each term in the query, we have TF, or a term frequency, which is a function of the number of times the term appears in the document. IDF, or inverse document frequency, which is how much weight we give that term overall, and that's actually across the whole corpus. Can't really see it in the yellow here. A query-specific boost function, so if you boost a term on the query, that's where it gets applied. And finally, another normalizer. But most of these we don't really care about. We require all query terms appear in the document, and we don't do any fancy boosting, so both the get boost and the coordination factor are constant for our queries. And this query norm is actually fixed for the query, so it's not going to change the relative ranking of two documents, given how we're computing it. So what we're left with are TF, IDF, and our normalizer. TF and the normalizer are both functions of a term document pair, so it's tied to a document, and it's really user-generated content to that point. If you put bag 100 times in something that's actually a pair of luggage tags, the most we can do is send you a nasty email saying you have mislabeled this, please fix it. The IDF, though, is actually a function of the corpus and something we can really play with because it's how important we consider things to be. Yeah, just to be clear, most of this is user content. IDF is really just a measure of rarity of the terms. And lo and behold, for this example, if we look at it, we find that the IDF of unique is slightly higher than the IDF of bag. So we think it's a slightly more important term. And if we look at the actual content of these listings, we find that these tags have unique occur a couple times and bag once, whereas the bag only has unique once and bag a couple times. Then because of how we're weighting these terms, lo and behold, the luggage tags look more relevant. But there's really an issue here, which is unique doesn't tell us anything. We sell handmade and vintage goods. Everything is basically unique. The number of times you say it, whether or not it appears, is kind of irrelevant. So, the obvious answer is, why don't we just add it to a stop word list? Resign it to the garbage bin with the, for, and of. And that would probably work for unique because it really is that useless for us. But what about handmade or blue? These are other things that tell you nothing about the item in question. 80% of our items are handmade, but what if you put it in your description instead of the title, or we use it for faceting instead of the retrieval part? We want it to be there, we just don't want it to be very important. So these kind of low information words that don't tell you anything about the object in question are useful for matching, but are really bad for ranking. So can we make some tweak to IDF? Can we change how this works, or just replace it wholesale? So just to sum up, IDF really ignores term usefulness and only considers term rarity. So, all right, that's our problem. What are we going to do about it? Really, if we're going to replace IDF, we need to have a good idea of what we want to replace it with and why IDF is good in the first place. So there'll be a little bit of math. You don't have to pay too much attention to it, though. This is kind of a canonical theoretical index. All of Solr and Lucene's tricks to make this fast and retrieval easy really just comes down to the fact you have this giant matrix of terms by documents. Each document is just a vector of length m of the number of times each term occurs. To speed up retrieval, we actually compute an inverted index, which is a map from the term to the documents it contains. Pretty simple. And we compute IDF by just taking one row of our index and the number of documents and running it through. This is the actual function that Lucene uses. So it's really easy. We're building an index of terms to the documents that contain it. We can just take that, sum over it, use the number of documents, and we're done. Really fast to do incremental indexes. You basically get it for free by doing retrieval. And it works pretty well. I mean, if it was terrible, nobody would be using it. One other thing we're running into around the same time is we're not sharding yet, but we might have to soon. Our index is continually growing, and it's getting to the point where we can't really manage on one machine anymore. And so now our nice, happy theoretical index is broken into two shards, one with some portion of the documents, and two with the rest of the documents. And how do we compute IDF here? Well, we can compute it for each shard, so we can sum up all the occurrences of jewelry and the number of documents in the first index, same for the second, but that's not really the same. We won't have, the IDFs won't be the same across the two shards, and they most importantly won't be the same as the IDF of the unsharded version. So our scores are starting to change. And since this is something we're looking at, it would be nice to solve this problem too. So what are our options? Well, we can ignore it. One of my coworkers put together a small simulation of sharding, basically controlling the number of documents per shard and looking at how the min and max IDFs from the distribution over the shards changed. And so when you have, between 10 and 100,000 documents per shard, you're looking at maybe a plus or minus 10% to your IDF scores compared to the unsharded true score. But once you get up to the 10 to 100 million mark, so 10 to 100 million documents per shard, it's kind of basically back where you were because you have a very rich sample. But that's the point you probably want to start sharding again anyway, because that's a lot of documents. We could have so we don't really want to ignore it, but we can temporarily. We could have the shards exchange stats, but then we end up with this consistency problem. If we want them to all have the same IDF, what if a message gets dropped? What if a shard disappears? There's a lot of coordination issues here. It's messy. Or we could just have some central source distribute the IDF, but then we're kind of back in the unsharded case. some central source has to have all of the documents to compute the true IDF. But this is also a real opportunity for us. Say we do have some central source compute it. Presumably we want it to be something that doesn't change much. This would be an ideal way to replace IDF entirely. We have some really expensive offline process to compute some better statistic, distribute that out, and hopefully it doesn't change, so we don't need to recompute it every 12 minutes. We can do it once a day or once a week and still get good performance. So as I said, my background is machine learning, and my hammer of choice these days for approaching problems is this concept of information gain. Goes back to entropy, but really it's just a measure of what does knowing a particular piece of information tell me about what I expect to see. So we use the Kale divergence, which has some very weird notation. But at the end of the day, we're just comparing two distributions. So the probability of seeing a particular term in a listing is P of x, and our conditional distribution, P of x given y, which is the probability of seeing some term x given we've already seen y. So we could spend some time reasoning about the formulas, but it's not particularly productive. It's a lot easier to just look at the results. So I computed the IDF and the information gain for all the terms in our corpus and pulled out, because we're looking particularly at unique and bag right now, what has a similar IDF. So they're all in the 4.3, 4.4 range. So one nice property of information gain is it's very similar to IDF in a lot of ways. 0 means no information gain whatsoever. It tells you nothing and just grows positively unboundedly. But in practice, it's actually a fairly similar scale to our IDF scores. So we went from unique and bag to being very similar to unique having 0.26 bits of information and bag having 1.24. So it's about 5 times more information contained in bag. And this makes sense. Bag tells us, we might see canvas, we probably won't see wood. Unique doesn't tell us anything. And you can see, most of these you can kind of make work. Like man, you're probably not going to see dress, but anything that's appropriate for men's clothing or accessories might co-occur with it. We can also go the other way. We've really dropped the information, or the quality, I guess, or the weight of unique, so what's similar to it? Well, 0.26 for unique, we have some colors, black, red, and white. Handmade, which is essentially a stop word, but not necessarily meaningless. 4, actually, when I was running the simulation, I didn't pull out stop words, so this is really encouraging, is we're kind of automatically finding things that look like stop words. And so just to come back to this motivating example of unique bag, if we use IDF, these luggage tags score higher, but if we were to swap out information gain, this bag would, because we're giving bag a much higher weight than unique in the second case. So seems promising. We know IDF ignores any sense of usefulness of a term, and we know information gain accounts for term quality, and also in the limit, the term with the most information is a unique identifier, so we do get some rarity factor in there too. So that's great. Information gain. What do we do? So we've done some work previously with kind of complex offline calculations and getting it into Solr. Some of my coworkers worked on what we call listing quality. So we have these search results, and we want to know whether or not there's something that are actually going to sell. There's a lot of things in the marketplace that won't ever sell, and it's not too surprising. The images aren't very good, the price is way out of line. Because it's user-generated content, we have to be a little more careful about how we're doing things. So we compare the performance of, say, this bag compared to other things that occur first in search. So there's no sense in comparing the first result in search with the 1,000th, because probably no one will ever see the 1,000th, or they won't click on it because they'll just be scrolling past it. And so we have some very complex jobs to do it, but at the end of the day, we suck in all of our logs, run a Hadoop, run some MapReduce jobs on Hadoop to produce a basically a listing quality score, so a map from doc ID to a float that we dump into HDFS. We have a cron script to copy that from HDFS to our master, a little bash script to copy that from the master to the slaves, and then we load an external file field. So we have some plumbing in place. We have some experience with this. What do we do about information gain? So to compute IDF, we only need one row out of our index. To compute information gain, though, we actually need, say, to compute the information gain of art, we need not only all the occurrences of art, but every term that co-occurs with it. So, and this could require basically our entire index to compute the information gain for a single term. So, and we would have to do this for every single term in our corpus. Very expensive. We're looking at, NM squared kind of computation. But we have a nice shiny Hadoop cluster that doesn't have enough running on it, so let's just brute force it. We can just put together a job. We use actually language a couple layers removed from MapReduce. But at the end of the day, that's not too important. All we do is we count all the terms in our corpus. We sync our databases to HDFS every night, so we have all the data there. We can count all co-occurring terms. This is actually incredibly parallelizable. Each document can be done independently. We can just do some joining and summations and clever tricks and just construct the distributions manually, and then just iterate over everything to compute the information gain. This takes maybe 2-3 hours depending on contention on the cluster, but at the end of the day, we get a file that maps terms to a very useful score. We can use the same simple set of tools to replicate it, and cron to copy it over periodically, a little bit of bash magic to get it from masters out to the slaves when a new slave starts up. But what do we actually do with it? We have this file on the slaves. We want to bake it into the similarity measure. So we implemented a similarity factory, which is a really kind of cool thing. So basically, at startup, the init will be called, and then things will be kept around, and periodically it'll request a new similarity measure from this factory, kind of standard Java pattern. So what we do is, in our schema, we get the parameters to this factory passed in. We know the prefix of the file that we're looking for, information gain. Our config can tell us where that actually lives in our file system. We can use Lucene's version file to get the most recent version. The original implementation of this, I was actually pulling things directly from HDFS. This is actually a lot more elegant because if a job fails, we can't access the data, we'll still have old replicas sitting around this way. So we'll always have some version of the file we can use. And then we really just scan it in and dump it into a private static map of bytes refs to floats. Then our actually similarity implementation just extends Lucene's default similarity. Because it's a nested subclass, it can access this private static map. And so at query time, it sees a term. If it exists in the map, it returns that as the IDF. Otherwise, it just calls parent.idf. There's basically no operational overhead. We have maybe 100,000 terms in our corpus, so this map is pretty small. It only gets loaded in basically once per JVM startup. But we want to set up to do some testing, so how do we actually implement this? Say we have a field title en that is our, the title of a listing in English. We just make a new one, title en info. We attach our similarity factory to it, set the parameter as the prefix of our file, make a new field. We actually copy over the contents of our existing field. So now we have two identically populated fields in our index, title en and title en info, that they have the same data, but they have different similarity measures attached. We can then produce an identical query that has the information gain version of the title and the non-information gain version. And at query time, we can decide which one to use. This lets us do some really easy A/B testing. So right, back to our little summary. IDF ignores usefulness. Information gain is a measure of usefulness. And Hadoop plus a similarity factory is really handy. But as I said, we really like experiments at Etsy. We deploy all the time, we deploy a lot, but we're very careful, particularly when it comes to things like this. We're changing a measure really deep in the system. Most sellers would have no clue where this actually lives, much less how to game it. And even a small change in our similarity measure can have a fairly drastic impact. So we need to go slowly. We had an idea, we've done a proof of concept. Our next step is usually a side-by-side for search changes. Then an A/B test, and eventually push it live. So side-by-sides are kind of a handy tool. It's, as the name implies, we basically just stick two sets of search results in front of the user, and they can pick either results A, results B, or neutral for which one they like better. We're doing pretty good on time, so I'm actually going to do a quick one with you guys just to demonstrate. So here is two sets of results for wedding dress. See a quick show of hands. Who thinks the result set on the left is better? Who thinks the one on the right is better? All right, pretty overwhelming. Next one, pearl necklace. Who thinks the results on the left are better? Who thinks the ones on the right are better? Okay, and who thinks they're basically the same? Yeah. And my personal favorite, cross stitch. Who thinks the results on the left are better? A couple people. Results on the right? Nobody? About the same?
What is the cross stitch?
Exactly. Yeah, it's, I don't know. It's something that involves stitching stuff. Yeah.
Stitching is an X.
Yeah, okay. The stitching is an X, very good. I work for XA, I should really know this. Great, so actually that was a little surprising. So in all of these actually, I didn't randomize this just to keep it easy. The left side was the IDF-based measure, and the right side was the information gain-based measure. So we see for wedding dresses, we have mostly hangers, a couple belts, and a few dresses thrown in. Under information gain, we have mostly dresses and one picture. I'm not quite sure why it's there, but certainly an improvement. Pearl necklace, overwhelmingly lack of decision. They're all pearl necklaces. You know, some are strands, some are singles, some have ribbons attached, but at the end of the day, it's kind of obvious. Cross stitch, though, is really interesting. And the results here were actually different than what I saw on the side-by-side, which is another issue with side-by-sides. So I would argue that the two sides are equally relevant. They're all either finished cross stitches or patterns in about the same frequency, but the images on the left are a bit better. You have some nicely lit ones, really centered images. And on the right, you have this one, which is a picture, it's a little blurry, picture of a girl holding a cross stitch of Britney Spears, slightly lower to her than her face and not quite in the center of the frame. I did this side by side internally with about 100 subjects randomizing, 100 queries, about a dozen subjects randomizing the sides, and talked to the people afterwards, and overwhelmingly, they chose the left results here because they didn't like this picture. It is a perfectly relevant piece of cross-stitch. She cross-stitched Britney Spears' face, but it's kind of a low-resolution picture. The lighting's not great. Why is she the center, not the thing she's selling? It's really kind of disconcerting, which leads to really an endemic problem at Etsy, which is relevant doesn't necessarily mean high quality and doesn't necessarily mean what a user wants to see. But we had a slight loss in the side-by-side. Information gain did slightly worse, and it was usually cases like this where the results were equally relevant, but there was an ugly picture thrown in there. So we went ahead with an A/B test anyway. So if you haven't seen or done an A/B test before, it's pretty straightforward. Every user is assigned randomly to a bucket, either A or B. We can set the percentage. It's persistent across log in, log out, clearing cookies. It's a consistent hash based on the user and the test. And so in bucket A, we showed all of the users IDF-based results. In bucket B, we showed them IDF or InfoGain-based search results. They had no idea what was happening. So we just did this in the background, put about 1% of people in the InfoGain bucket. And the results were a little disconcerting. We saw small but statistically significant decreases in click-through rates, page views. If we kept going, probably conversions too. Nothing overwhelming, maybe a 1% drop, but it really highlighted one of the big problems here, which is we were kind of asking the wrong question, or at least answered the wrong question, because we can show the results are actually more homogeneous. I looked at the distribution of categories in the result sets and co-occurring terms in the result sets, and they were lower with information gain, meaning the items are more kind of self-similar, probably more relevant to the query, but we actually have a file of quality scores based on user click behavior, and overwhelmingly the information gain ones had lower quality. Probably because they had never really been surfaced to users before. And it would take a while for this to come down. So in some sense, this was very successful. We found a way to improve relevancy, but it's not something launchable because it's conflicting with a business goal. So I suspect the next steps for me for a couple months is parameter tweaking. We have relevancy signals, quality signals, some recency signals in there. And because we made a change to the relevancy algorithm, these need to be rebalanced. This might take weeks or months of experiments, small percentages, careful tweaking. Because we saw dramatic improvements in queries like wedding dress, there's a real feeling that we need to be doing something like this, but we need to rebalance the rest of our search to adapt to it. But this core idea of having a really expensive computation run offline in Hadoop and then sucking it into Solr can lead to a lot of really interesting things. In fact, when I heard the next conference was in Dublin, I have an idea for what I want to try and present. So there's a technique, it's pretty common in academia, as far as I know, nobody really implements it though in real systems, called latent semantic indexing. The simple version is in a standard vector space model, documents are sparse vectors in term space. So most terms don't occur in most documents, so you have mostly empty vectors with a few occurrences. Latent semantic indexing takes these, does a eigendecomposition, remaps these sparse vectors of terms to dense vectors in some concept space. These don't necessarily cleanly map to concepts, but it's called that. And you end up with fairly dense vectors and a transformation matrix going from your m-dimensional term space to your r-dimensional concept space. And really, this is just going to be a 100,000 by 100 or by 1,000 entry matrix. It's probably going to be fairly sparse itself. We can just do a similar trick we did with the similarity factory, copy this over, load the file at index and query time, perhaps in our analysis chain, and do this remapping on the fly. So suddenly, we've gone from the elements in our index being terms to being these abstract concepts. Obviously, this will require a lot of testing. I'm not really sure how Solr and Lucene would perform, suddenly having a dense, pretty much solid matrix instead of a really sparse matrix. But the nice thing about this, because you're doing dimensionality reduction, you're losing some of the kind of noisy, less important things. You're getting terms collapsing to canonical kind of clusterings like jacket, coat, might all end up as the same like cluster that you can ascribe a name to if you want, but really doesn't have one. So I think there's a lot of kind of interesting directions we can go with this, using basically Hadoop, built-in Solr, and a couple shell scripts to tie them together. Yeah, that's all I have. Thank you. Yeah. Can we do the information gain in real time instead of like a batch once a day? We have two distributions that are both being updated somewhat independently inside a log, which makes an incremental update really difficult. We have to keep around a lot of the statistics and take an exponential and do a log, and we'll lose some precision that way. And in theory, this is more of it's less of a corpus statistic than it is some hopefully intrinsic measure of the words in our domain. So ideally, it'll change less quickly. So find, we have a lot of seasonal words. So like wool is a much more common term in the winter than it is in the summer. But we'll probably find wool and sweater and a lot of other kind of heavy wintry things are dropping out at the same rate. So the information gain will be roughly the same. There'll just be fewer examples in the corpus. We've gone through a couple versions. We have a really nice analytics stack built on built on tools, built on cascading, built on MapReduce. But we do, our usual ways are strict funnel analysis. So search, click on an item, and buy it with no intervening similar events. We have some standard A/B testing tools that do a visit level conversion rate. So visits where a search occurred at, converted at 3%, or like 3% of all visits with a search converted. And then we A/B test and look at that same kind of visit level statistic. For our ad system, we actually do a kind of delayed attribution. So if you click on an ad and buy something from the same shop within a time window, we will attribute that to seeing the ad. So we've gone through a couple different models of it. So one of the things about the way we compute information is it's not really looking at distance. We actually index fairly small parts of the document. The title, certain tags are given the most weight. But users, the thing is, power users have picked up on this. And I mean, they figured out that I think the first 8 words of our title are more heavily weighted than the rest. And we'll stuff the first 8 words with common search terms. So it's kind of almost an adversarial search process. We are trying to surface anything that's good, and sellers are trying to get themselves to the top. And so this kind of, in some sense, shook it up too much. There were listings that were 10, 15 pages deep before because the people didn't really know how to game the system, but we downweighted things like wedding dress hangers, which have this really unfortunate property. They convert pretty well because you're not going to buy your dress from some random person. You're going to buy a nice hanger to give to your friend after looking at pretty dresses on the site. Same thing with desks and desk calendars. You're much more likely to search for desks, look at desks, and then buy a calendar than you are to actually buy the thing you seem to be searching for. So in some sense, there's also a user experience problem. One way we might want to take this is we have that ad row at the top. It's still items on site. If that was kind of complementary things that weren't necessarily what you were looking for but are related to it, so the hangers, the calendars, and then the organic results were just highly relevant to the entity you were searching for, that might be a good way of kind of splitting out the two and making sure you had a good search experience and something you were going to buy as well. All right, well, thank you all for coming. Oh. All right.